Good morning, everybody. Thank you very much for having me here today, and thank you to the traditional owners, past, present and emerging. Just acknowledge them. And it's a bit of a thrill today. This is the first time I've presented in this brand new theatre, so I'm clearly moving up in the world. And also just apologies, I've got to breeze in and breeze out today. I'm pretty much having holidays at the end of this week and I've got a lot of work to get through. Director's been riding me pretty hard. And the director's our previous presenter. So, what did I just change that there? Okay, so I'm going to just talk about, that's actually given me the opportunity to revisit some work that we've been doing for the last, work that we've done rather 10 to 15 years ago. And that's really looking at the sediment budgets in the Burdekin River, including what's been going on within the Burdekin Falls Dam. So what do we know about our wonderful Burdekin River? The current export rate is around 4 million tonnes per year. But of course, the averages in the Burdekin's a bit silly because, 1 year it might be 100,000 tonnes in a very dry year, upwards to 15 to 20 million tonnes in a very big wet year. We know there's been an increase in those sediment loads of roughly 4 to 10 times since the arrival of Europeans and the development of the catchment. This is through a lot of different forms of evidence, through modelling, through sediment cores, and through sediment erosion studies within the catchment. It's probably closer to 8 to 10 times higher prior to the dam and probably about 4 to 5 times higher since the dam. But of course, if we want to do our budgets of when the sediment's moving in the river, we really want to be out there where the river's flooding so we can collect the samples, because this is the period where the sediment is being transported through the system. And this is just an example at the Burdekin Falls Dam spillway in 2009, where it was going about 6 metres over the spillway in that particular year. So it's about the second highest peak that we've had for the Burdekin. The highest was in 1991. So this is where the water's transporting all that fine sediment through. So we started looking at, where's the sediment coming from in the catchment and how much sediment's being trapped in the dam and how long is the dam going to last before it silts up. So they're the questions that I'll hopefully address for you today. So with the help of a project through the North Queensland Dry Tropics, we were out sampling the major tributaries of the Burdekin River where we've got flow gauges. So we can look at the concentration of sediment in the water and the amount of water going through, and we can calculate a sediment load. So we go out to sample at the Macrossan Bridge, just on the way out to Charters Towers, and that captures the upper Burdekin River arm. We get on the Gregory Developmental Road and sample Cape River along the Gregory Developmental Road where there's a flow gauge there as well. We sample the Ballyando River at Ballyando Crossing, and we sample the Sutter River on the Bowen Developmental Road. And we've got a flow gauge there, but we also have a flow gauge a little bit further downstream at St Anne's that captures both the Ballyando Sutter. So with those measurements, we can measure the amount of sediment that comes into the dam. And we had our colleagues at Sunwater who kindly captured samples for us on the dam overflow waters so we could quantify the amount of sediment going over the spillway. So from that difference, we're able to work out how much sediment is being trapped in the dam. So this study was done over 5 years from 2005-06 wet seasons to the 2009-10 wet season. And then we also have people sampling for us off the Inkerman Bridge there at the end of the river, where we capture the sediment load going out into the marine environment as well, which is a much longer record of data we've got from there now. So the difference essentially of the sediment load going through the Burdekin Dam and the difference at the end of the river gives us the amount of sediment coming from that area below the dam. So just a couple of other pretty pictures. Didn't want to show up my director, but I've got a better photo of the Macrossan Bridge that he just showed. This water's now over 6 metres over the bridge there on the way out to Charters Towers, and not getting through there. And it also raises, where do you get an accurate sample from here of the sediment in the water? And thankfully, in that particular year, we linked up with the Queensland Rail guys, and the railway bridge just downstream of there They took us out on the railway line, and we collected a sample right from the middle of the river. So we got a really good representative sample of that water on that day. We wanted to take extra samples, and they said, oh, well, you can stay for a bit longer. There's a train coming by in 5 minutes. You can just go on one of those overshoots. We're like, no, we're right. We'll come back. But from this study, we're able to look at the stream flow contributions from those major tributary arms from the Burdekin and the average sediment loads over that 5-year period. And here you can clearly see not only the flow dominance of that upper Burdekin arm into the dam, but the sediment load dominance from that upper Burdekin arm into the dam. So here, upper Burdekin, we call it at Selheim or at that McCrossan Bridge. About 66% in those 5 years of sediment delivered to the dam was trapped. And then we also had quite a big contribution from the lower Burdekin. So, and you can see here, the export here was quite a bit higher than that long-term average of 4 million tonnes that I showed you. I'm not going to explain this slide, the graph at all, but what I can say is we're pretty pleased we're in the right place at the right time, because the amount of sediment trapping in the dam in a tropical reservoir is very rare for tropical environments. And we're able to put this into empirical equations or algorithms that have been developed from temperate environments, largely from the USA. And the modelling has shown that the tropical environments just don't play the game. But we're able to modify this to look at a daily flow step, which we're able to better predict the amount of sediment being trapped in the Burdekin Dam through a daily model. So, and this now can be applied across the world, and particularly for tropical reservoirs. So we can predict the amount of sediment being trapped by a dam by just having the daily inflows into the dam, the capacity of the dam, and knowing the load of sediment coming into the dam. We can say this is roughly how much sediment's being trapped in the dam through our dam trapping calculator. So going through what's the particle size, this is where the story, I guess, really comes together a bit more, because the dam preferentially traps certain particle sizes over others. So this is our particle size in microns. So 1 micron is 1,000 millimeters. So that's just to give you a bit of an example of how fine that is. And we've got the load of sediment going in. This is a plot of the actual load of the different particle sizes of the sediment going over, while coming from the different tributary arms, and what's gone over the overflow here in this dotted line, and the amount trapped here in this dark solid line. What we found is particles less than about 1 micron or half a micron was just not trapped by the dam. This is our colloidal particles by definition, which is what makes the river turbid all year round, this less than 1 micron particle size. And they're largely from that Valiendo Sutter arm, but there are tributaries in the upper Burdekin that contribute this colloidal material as well. The sort of clay-sized particles from about half a micron to 5 microns, about 50% of that material is trapped. We go up to the 5 to 30 micron part, 75% is trapped. And virtually everything above 30 microns is captured by the dam. So this is all our sand that's delivered from the upper catchment is entirely trapped by the Burdekin Dam today. So just a summary of where the sediment's coming from. This is our fish-eyed view from the very first Burdekin water quality improvement plan run by MQ Dry Tropics. Always love this image. Our sampling sites up in the catchment. So dam traps about 70% of the sediment delivered from the upstream area. This upper Burdekin contributes about 85 to 95% of that sediment consistently over years, even when there's bigger flows in those southern catchments, still contributes by far the highest amount of sediment. The Valiendo Sutter Cape, in contrast, 1 to 10% each of the sediment supplied to the dam, which leaves the catchment area below the dam contributing upwards of 50 to 80% of the end of catchment load of the Burdekin River. So that's the management implications are saying, well, if you wanted to invest your money in erosion remediation efforts, you invest your money in that catchment area below the dam, which is largely the Bowen Broken Bogey catchment. We also had a community monitoring program where a lot of landholders, largely graziers in the region, would sample their local tributary and stream over about the 6-7 year period throughout the Burdekin. And so the bigger the circle, the bigger the sediment concentration that we're seeing. So it's actually where the sediment's coming from, we can get a finer scale level of the sources as well. And recently, we've been involved in this Landholders Driving Change partnership with North Queensland Dry Tropics, where local graziers have again started sampling a few more extra streams in that little Bowen Broken Bogey catchment. So we've got some extra data to add to that part as well. So the two key areas is that upper arm of that upper Burdekin catchment, that northwestern arm, and largely the Bowen and Little Bowen area. And when we look at the geological map there, it really comes down to the old sedimentary terrain and basaltic type rocks in quite steep and wetter environments of the Burdekin that's delivering some of the elevated sediment loads. Now, just quickly on the dam, I know I'll probably going to get kicked off in a moment. This was the original aerial photo of the dam, Burdekin Dam, before as it was being built, and the there, and we have done a fair bit of work within the dam and looking at how much it's being trapped. We've taken sediment cores in the dam where we can see the laminations of little layers of sand as we go further upstream where the big flows have come in. And we can actually do swath mapping to see the original channel in the Burdekin Dam still exists. But with our dam trapping calculator and the sediment cores in the dam, we're able to calculate how much sediment's infilled the dam and how long it's got before it completely silts up, which was a pretty interesting question because what we call the useful life of a reservoir. And dams of similar sizes in China and India have a useful life of only about 20 to 50 years before they silt up and they're no longer useful. What's the answer for the Burdekin Dam? Well, John gave it away. It's about 276 years, so we've got some time, and this is the current design of the dam. So much bigger loads really in the China, India examples coming in. And just finishing on a more positive note of some of the work that's going on is looking at a lot of the erosion in the Burdekins coming from subsurface and gully erosion, work from CSIRO looking at how to regenerate sort of the smaller gullies. We can reduce the stream flow going into that gully head and then we can vegetate over this gully. And there's some more spectacular works going on through the major integrated project in the Bowen Broken Bogey catchment where we've got these massive gullies in the system. It's like a mine site rehabilitation job where the gullies are being essentially levelled and the soils are being treated and that land's being completely rehabilitated. That's an example of the Mount Wickham site through the Landholders Driving Change project. And there's another example at Strathalbyn Station, which is run through Green, Australia. So that's a before and after shot. So pretty spectacular changes in the landscape. Some of these gullies are probably contributing about 1,000 tonnes of sediment per year. And just before I finish, I was just going to say, if you want any further information, we did what was called the Burdekin sediment story, looking at work going back from the end in the marine environment all the way back up to the catchment sources. And as a bit of a communication product through this Burdekin sediment story report, we produced a lot of conceptual diagrams that went out from, where's the sediment going in the marine environment, how's it being carried, and then where's it coming from in the catchment, and what's the different erosion sources and what we can do about it. And so there's a few examples of the catchment sources, what that looks like, the erosion in grazing lands, and what we can do about it. So I'll leave it there. Thank you.